Today, our goal is to talk about linear transformations. One of the important applications of linear transformations is in machine learning and deep learning. In machine learning and in deep learning, linear transformations play a fundamental role in various aspects, especially dimensionality reduction and feature transformations. A linear transformation are usually used to transform input features into a new space where they might be more easily separable, or it helps to identify the pattern. This is particularly useful in tasks like classification and clustering. For example, in PCA or principal component analysis, linear transformations are used to project data points onto a lower dimensional subspace. For example, in self-driving cars, it requires fast and efficient process of sensor data to make timely decision and control actions. In dimensionality reduction technique like PCA or principal component analysis, it can help reduce the computational burden by reducing the number of features to process while retaining essential information. This can enable self-driving cars to perform complex tasks like object detection, tracking, or path planning in real time. So as you see, we have real-world scenario. The data are like this. These are the images that a machine can see. They start detecting objects, the lanes, or any object on the road. And it requires a timely and fast and efficient method to detect these objects. One of them is using PCA. Let's go back to the definition of a function. A function like f from a set like x to a set like y denotes by f from x to y. It is a relation from x, which is called the domain, to y, which is called the codomain. It satisfies two important properties as a function. First of all, every element in x is related to some element in y. So it's not exactly all of y. And two, no element in x is related to more than one element in y. So you have uniqueness as well. Therefore, given any element like x in the first set, there is a unique element in y that is related to x by f. If we call this element y, then we say that f sends x to y, or basically you can write it this way. F as a machine maps x to y. You can also write it this way. X goes to y by f, or f maps x to y. A unique element to which f sends x is denoted by f of x. We have different methods of calling f of x, or the output of f for input x, or the value of f at x, or the image of x under f. So when you're dealing with a function, you have different methods working with function f and basically calling f. So you have a set, which is the domain. Function f takes elements from domain and it maps them to codomain, but not all of the codomain might be used. So we define the range. The range is the set of all output values that are connected to x values in the domain. So this visualization helps us to make sure that we know it's not necessary that all elements in the codomain are part of the range. It's not necessary. You have a function that maps elements in the domain, everything in the domain. That's why you see all of the elements in the domain are taken to another set, which is called the range. And this set is a subset of the codomain. The set of all values of f taken together is called the range of f, or the image of x. So if this is set x, then this is the image of x, which we call the range. So basically, this is going to be f of capital X, which is part of a larger set that we call Y. So that's the difference between X, Y, and f of X in general. The range of f is the image of X under function f, which is the set of all Y values in Y such that X is equal to f of X for some X in X. Given an element like Y in the codomain Y, there may exist elements in X with Y as their image. If f of X is equal to Y, then X is called the PreImage of Y. We can also call it an inverse image of Y. The set of all inverse images of Y is called the inverse image of Y. Symbolically, we represent it this way. The inverse image of Y is a set including all of X in the domain such that f of X is equal to Y. If f maps X to Y and is a function, we can take subsets of the first set. A is a subset of X and C is a subset of Y. Then we have the following definition. F of X is the set of all Y values such that Y is equal to f of X for some X in A. So f of A, which is the image of A under function f, is all Y values such that Y is equal to f of X for some X in A. So again, function f maps X to Y. The inverse image of f maps Y to X. Basically, function f takes X values and maps them to Y values in the range. Range is a subset of the codomain. So this is your set X, and this is your set Y, and this is the range of the function. The inverse image of C is the set of all X values in the domain such that f of X belongs to C. Again, f of A is called the image of A, and inverse image of C is called inverse image of set C. So if set A is a subset of X, including X1, then function f takes elements from A and map them to f of A. Now, let me change the color. If you take C as a subset of Y, this is your C. inverse image is defined. Inverse image takes elements in C and map them to some elements in X. So inverse image of C is all X values such that f of X belongs to C. These are the definitions and the differentiation between F and inverse image of F. Now with this definition, remember the definition of one-to-one function as well. We say that a function is one-to-one or injective if and only if y values are different from each other, then you can conclude that x values are. If you have same y values, you get same x values. If x values are different from each other, you get y values different to each other. So you have if and only if condition if you have finite sets. x1 is not equal to x2 if and only if y1 is not equal to y2. So again, symbolically, function f from x to y is 1 to 1 if and only if for every x1 and x2 in the domain, if y1 is equal to y2 or output values are equal to each other, you can conclude that x values are equal to each other as well. Or if x1 is not the same as x2, you can conclude that output values are different from each other. We say that a function is onto or surjective if and only if, given any element like y in y, it is possible to find an element like x in the domain such that y is equal to f of x. Symbolically, function f from x to y is onto or surjective if and only if for every random element that you take from the codomain, you can find a value in the domain such that f of x is equal to y. Given these definitions, we are going to introduce a linear transformation. Let T be a function that maps a vector space like V into another vector space like W. So instead of x and y, we're using v and w. This function is denoted by t that maps y to w. V is called the domain of this map, of this function, and w is called the codomain of this function. If you take a vector in V and take another vector in the codomain W such that T maps V to W, then W is called the image of V under T. So V is mapped to W and W is called the image of V under function T. The set of all images of vectors in V is the range of T. The set of all vector V in the domain such that TV is equal to W is called the preimage or inverse image of W. So again, now you have a function. This function is now denoted by T. It maps V to W. Again, guys, W is the codomain, is the larger set. It's not necessarily the same as the range. The range is included in the codomain. Your function takes V and map them to elements in the codomain or the range. So with these definitions, for any vector V, we have the following function. Function t maps v1 and v2 to v1 minus v2 and v1 plus 2v2. Question says, hey, find the image of v. Let us begin. For v, which is -1 and 2, it means that v1, the first component, is -1, and the second component is 2. So we just need to plug them into the definition of this function, which is -1 minus 2. This is -1, and this is -2, comma 1 plus 2 times 2, which is -3 and 3. So basically, this function takes -1 and 2 in the domain and gives you another vector, which is -3 and 3 in the range. This value belongs to the range of this function. If I ask you to find the image of v, v is 0 vector. The components are 0 and 0. So if v is equal to 0 and 0, then t of 0 and 0 is equal to 0 minus 0, and 0 plus 2 times 0, which is happen to be 0 and 0. So this function takes a 0 vector and gives us 0 vector back. The next question says, hey, find the pre-image of W. Guys, now W is in the codomain, -1 and 11. Take a look. By definition, T of V is equal to V1 minus V2 and V1 plus 2V2, which is equal to -1 and 11. Well, it's not that difficult to see that. V1 minus V2 is -1, and V1 plus 2V2 is 11. This system has unique solution. What you can do, you can basically multiply the first equation by negative. Get negative V1 plus V2 equals to 1. If you add this together, you get 3V2 equals to 12. So V2 becomes 4 and V1 is 3. So you can say that, hey, the pre-image or inverse image of -1 and 11 consists of single vector 3 and 4.